Welcome to the channel. I'm Carlos Ortega, and I'm excited to explore the amazing worlds of physics and chemistry with you.
When we watch astronauts take graceful, bounding steps across the lunar surface, it looks as though the physical rules governing the human body have shifted. A traveler with a mass of 50 kilograms on Earth steps onto a scale on the moon, and the reading drops to a fraction of its normal number. Did the physical structure of their body shrink? Did they lose actual matter during the 240,000-mile journey? The matter remains. If you set a dinner table on the moon and yanked the tablecloth out from under the dishes, those plates would resist the movement and stay put, exactly as they do on Earth. The physical resistance to acceleration, or inertia, hasn't changed. This observation highlights the interaction between two variables, the material we are made of and the strength of the celestial body pulling on that material. To understand how our biology interacts with the cosmos, we have to look past our earthly biases and separate two different concepts, mass and weight. Mass is your physical inventory. It is the constant amount of matter contained within your body. In physics, this is a scalar magnitude. It is a standalone measurement that operates independently of your direction, your position in space, or external forces. Because mass is an extensive property of matter, it is tied to physical size and quantity. If an object has a mass of 1 kilogram, the only way to change that measurement is to physically remove a piece of it. For over a century, we defined a kilogram using a platinum cylinder locked in a French vault. Today, science defines mass using the Planck constant, a universal constant of quantum physics. Your mass is your biological inventory, a physical constant whether you are sitting in your living room or floating in deep space. Weight is an action. It is the force of gravity pulling downward on your mass. Unlike mass, weight is a vectorial magnitude. For weight to exist, it requires both an intensity and a specific direction of pull. This formula shows the mathematical engine governing our bodies. Weight equals mass multiplied by local gravitational acceleration. When we plug in Earth's local gravity, accelerating at 9.8 meters per second squared, the output is the heavy, grounded sensation we experience. If we swap that local variable for the moon, where acceleration is just 1.622 meters per second squared, the pull is 6 times weaker, even though the mass remains the same. The tools we use to measure reality reveal how these forces differ. Take the classic balance scale. A balance scale works on the moon because it compares the intrinsic mass of one object against another, ignoring the local gravitational field. Compare that to a dynamometer or a spring scale. It measures downward force in newtons. On the moon, the exact same object lacks the external pull required to stretch the spring to its Earth-based reading. The bathroom scales we use every day don't measure our physical bodies. They measure the specific pull of planet Earth. Our concept of heaviness is a strictly Earth-biased illusion. In a multiplanetary future, the physical sensation of our weight will change every time we enter a new planet's orbit. Gravitational pull is a localized physical interaction between two objects. Through all of those planetary transitions, the physical matter composing your bones, muscles, and tissues remains untouched by these shifting external forces. The force pulling you down belongs to the planet beneath your feet, but your mass is a universal constant that belongs to you.